Hello everyone, my name is Sachin Singh. I am a final year student of Civil Engineering Department at Faculty of Engineering and Technology, University of Lucknow. I am here to present a seminar on the topic Prevention of Foundation in Earthquake Prone Areas. Table of Content. First, we will know about introduction, then type of seismic waves, earthquake prone areas, type of foundation used in earthquake prone areas, causes of foundation failure, ways to prevent foundation failure, then we have case studies, and at the last we have conclusion. Moving to our next slide, we have introduction. An earthquake is when the ground shakes and moves because of powerful sudden energy burst under the earth's surface, which can cause building and things on the ground to wobble or even break. Preventing foundation failure in earthquake prone areas is crucial for safety and strong infrastructure. In urbanized earthquake prone regions, we need to use smart foundation design and construction methods. Our goal is to find and share new techniques, technologies, and information for building safer earthquake resistant communities. We want to create a future where seismic threat don't hinder human progress and safety. Type of seismic waves. There are two types of seismic waves. They are body wave, which travel through the interior of earth, and second one is surface wave, which move along the surface of the planet. Type of body waves. P wave in an earthquake are super fast and act like a loud thunderclap, pushing and pulling on rock as they travel, just like sound wave with air. They can move through both solid rocks and fluids. S wave. S wave in an earthquake shake the ground from side to side, like wiggling a rope. They travel only solid rock and are slower than P wave. When you feel side to side shaking during an earthquake, it's because of S wave. Type of surface waves. Love wave in an earthquake create strong side to side shaking, moving like a rug being shaken. They travel only through solid rock and can't pass through liquids. Relag waves in an earthquake create rolling and ripping motions on the ground surface like ripple in water. They move slowly but can cause strong shaking during earthquakes, traveling through both solid rocks and fluid beneath to earth. Here we have all type of graphical representation all of all type of waves. Earthquake prone areas. India is divided into several seismic zones based on the livelihood of earthquake. These zones are classified using the seismic hazard assessment, considering factors such as historical earthquake data, tectonic plate boundaries, and geological conditions. The Bureau of Indian Standard has classified India into four major seismic zones: Zone 2, Zone 3, Zone 4, Zone 5, and Zone 5 being the most earthquake prone. In Zone 2, we have cities like Kurnool, Vishakhapatnam, Nagarjuna Sagar, Bhilai, Raipur. In Zone 3, we have cities like Agra, Bareilly, Kanpur, Lucknow, Varanasi, Durgapur. In Zone 4, we have cities like Patna, Chandigarh, Delhi, Shimla, Amritsar, Dehradun, Nainital, Roorkee. Type of foundations used in earthquake prone areas. In earthquake prone areas of India, several types of foundations are commonly used to ensure the stability and safety of structure during seismic events. Here are some common type of foundations used in earthquake prone areas of India. First is isolated footing. They are like strong support feet for a building, spreading the weight and protecting it from shaking during an earthquake. Second, we have combined footing. They are similar to isolated footings but connect multiple columns, helping the building stay stable during tremors. Now we have pile foundations, long sturdy pillar buried deep to support the building and resist earthquake forces. Next, we have pier foundations, strong vertical column that hold the building up and protect it from earthquake movements. Next, we have strap footing, horizontal support beams connecting isolated footings, helping the building withstand ground movement during earthquakes. Next, there are shear walls, special walls designed to resist sideways shaking during an earthquake, enhancing the building stability. Next, we have mat foundation, which is also known as raft foundation, a large flat foundation like a thick mat under the whole building, providing stability during earthquake. Causes of foundation failures. Isolated footings. Failure can occur if they are too small or weak to support the building's weight during an earthquake. Combined footings. Insufficient size or strength may lead to failure as they can't handle the ground movement efficiently. Mat foundation, raft foundations, inadequate thickness or reinforcement can cause failure during strong earthquakes. Pile foundations. Piles may fail if they are not driven deep enough or if the soil can't support them during shaking. Pier foundations. Weak construction or inadequate design may lead to pier failure in earthquake prone areas. Grade beam, strap footings. Insufficient connection between isolated footings can result in failure during seismic activities. Shear walls. If shear walls are poorly constructed or not properly designed, they may fail to resist earthquake forces. Now, in the next slide, we will know about ways to prevent foundation failure. Building strong foundations. Use well designed and robust foundation structure that can withstand ground shaking. Proper sizing. Ensure foundations are appropriately sized to support the building weight and resist earthquake forces. Reinforcement. Use reinforced material and construction technique to enhance foundation strength. Deep pile foundations. Drive pile deeper into the ground to reach stable soil layer for better support. Seismic design. Employ earthquake resistant design principle and follow local building codes. Regular inspections. Regularly check and maintain foundation to detect and address any issue promptly. Shear wall implementation. Properly design and construct shear wall to resist sideways forces during earthquake. Case study 1. Palace Royal Tower, Mumbai, a modern marvel of earthquake resistance construction. Background: Mumbai, India is a prone to seismic activity due to its location near the tectonic boundary between the Indian plate and the Eurasian plate. In this dynamic environment, the construction of tall buildings present unique engineering challenges, including ensuring the structural integrity and earthquake resilience of skyscrapers. The Palace Royal Tower is a high-rise residential building located in heart of Mumbai. It stands at 320 meter, 1050 feet and comprises 68 floors, making it one of the tallest building of India. Challenges: seismic activity. Mumbai is classified as Zone 3 in terms of seismic activity, which means it is prone to moderate earthquake occurrence. Buildings such as tall structure in this zone required careful consideration of earthquake resistance design. Soil conditions: the tower is located in an area with varying soil condition, including soft marine clay and basalt rock. This necessitated a foundation design that could accommodate these different soil type. Solution: the construction of Palace Royal Tower employed a range of modern engineering techniques and earthquake resistant features. Deep file foundation: given the varying soil condition, a deep pile foundation was used to support the massive weight of skyscrapers. This type of foundation extend deep into the stable bedrock below, providing stability and reducing the risk of settlement during an earthquake. Reinforced concrete core. The core of building features a reinforced concrete structure that act as a vertical support system. This core enhances the tower ability to withstand lateral forces generated during an earthquake. Damping systems. The tower incorporate tuned mass damper and other vibration control devices to reduce away and oscillations during seismic events, enhancing the comfort and safety of occupant. High strength materials. High strength material High strength material and steel were used in construction, providing greater resistance to seismic force and ensuring the building durability. Outcome: this case study highlights the importance of incorporating earthquake features in the design and construction of modern building, especially in areas susceptible to seismic events. It demonstrates that innovative engineering solution can allow for the safe development of tall structures in earthquake prone regions like Mumbai, India. Case study 2: the Lotus Temple, New Delhi, innovative isolated footing for a modern architecture icon. Background: the Lotus Temple, officially known as Bhaiya House of Worship, is an iconic modern architectural masterpiece in New Delhi, India, designed by Iranian Canadian architect Fariboz Shaba. This unique structure is renowned for its distinctive local lotus flower like shape and serves as a place of worship and meditation for Bhaiya faith community. Project overview: architectural innovation. The Lotus Temples, designed in a feat of architectural innovation, it consists of 27 freestanding marble clad petals arranged in the shape of lotus flower This design required innovative foundation solution to support the building weight and ensure its structural integrity. Challenges: unique shape. The lotus temple unique design with its curve not uniform shape presented a challenge in distributing the building's weight evenly to the ground. Soil conditions. The site on which the temple was constructed has varying soil condition, including both hard and soft soil layer. This necessitated a specialized foundation design. Solution: the construction of Lotus Temple involved in implementation of isolated footing as a key structural element. Isolated footing. Isolated footings are known as spread footings were employed to support the load of individual structural petals. These found footings were specially designed to match the irregular shape of the petal columns. Variable depths. The isolated footings depth varied to accommodate the varying soil condition. In area with soft soil, deeper footing were used to provide stability. Reinforced concrete. The footing were made of reinforced concrete to ensure strength and durability. Outcome: this case study showcases how reactive and adaptive foundation solutions such as isolated footings can be used in the construction of modern architectural marvel like the Lotus Temple. The success of this project not only serve as an architectural inspiration but also highlights the importance of tailored engineering solution to meet the demand of unique and innovative architectural design. At the last, we have conclusion. In conclusion, the prevention of foundation failure in earthquake prone regions is vital for safety and infrastructure resilience. India's seismic zone necessitate smart foundation design employing various types like isolated footing, pile foundations, and shear walls. Case studies like Palace Royal Tower and Lotus Temple illustrate modern earthquake resistance construction to ensure safer, more resilient communities. It's crucial to invest in well designed foundations, adhere to seismic design principles, and conduct regular maintenance, ultimately achieving a world where seismic threats don't hinder human progress and safety. Thank you.